There are different types of sort of pictorial representations you can make of data, and some of them you can incorporate more than one variable, and some are a little bit more difficult to do that. So one I just want to show you is a graph. One type of graph is a bar chart. And I'm sure you've seen bar charts before, but I just wanted to sort of show you an example of how you can incorporate multiple variables into one bar chart. So bar charts are, you can know immediately it's a bar chart if you have these solid bars. They're separated by spaces, so they're not touching, and they're really good for nominal level variables or really any discrete level variables, because you need to be able to like show the different categories. So this has, so GPA would be the dependent variable here, and so it has two independent variables. It has gender and the year of school. So right off the bat, looking at this bar chart, we can see, and I mean, this is all pretend data, so this is just to show you what it could look like. But right off the bat, we can look at males versus females, and it seems to be that females have higher GPAs than males overall. So that's one pattern. But then we can also look at the pattern in terms of what year of school that these students are in. And it seems to be, this is year 1, year 2, year 3. So for both males and females, GPA tends to increase as they go from year 1 to 2 to 3. So the longer you're in school, the more your GPA will increase. But at every level, females tend to be higher than males. So that right off the bat, we can look at this and sort of see what what the variables are doing, both sort of independently and as they relate to GPA, but also when you put them together. So it's an interesting picture that you can see pretty quickly with a bar chart like that. So then a histogram is another kind of graph we can use, and it's like a bar chart, but it's more of you would have a count. So you have a count on the side here. So really it's like frequency. So a histogram is about frequencies. And so we're back to only one variable here at a time. So in this case, it's the height. So we're looking at heights of 3,000 adult English male criminals measured around 1900. So histograms are like bar charts, but you see now that the bars are adjacent. They're touching, no gaps. This is really good for continuous level variables, because what you would do is you would see how many people in your sample are at each level of the variable. So, we would look and see that, people who are reporting as 5'5", there's about 450, 460, something like that of our sample. So we can look at this, and this variable, we can look and see that it's fairly normally distributed. This would be our center, our measure of central tendency would be somewhere right there. And then, our variability, we can look at how spread out it is. It looks like maybe it's a little bit leptokurtic because it's a little bit more peaked, and it's not skewed at all. So we can see that just by sort of looking at this and seeing what it looks like on the histogram. So the histogram is a good way of visualizing each variable using sort of the different measures to describe that variable. And then we have a frequency polygon, and a frequency polygon is very similar to the histogram. You would use this with the same types of variables that you would use histogram for. So typically you would use this for continuous level variables. So this is just, again, it's frequency, so it's counts, and we have a test score on whatever the test is. So test scores, it looks like we had, either 0 or maybe 1 person kind of at the lowest here, which is 35, and about 1 at the highest, which is 175. And then we can kind of go up and see at each measure, so at each of these numbers where we have a point to plot from our sample, you plot it on the frequency polygon, and then you plot all these points, and then you have this continuous line that connects the points. And so it kind of gives you, again, the reason you put the continuous line is literally it's to connect the dots to make it so that you can see what the curve looks like for your variable. Because if you don't connect the lines, you just have a bunch of dots, you can kind of still see it, but it's a lot harder. So this allows you to kind of be able to see what the curve of your variable is. And remember though, with any graphs, when you're using any kind of pictorial representations like this, if they are misused, they can distort the distribution rather than accurately display the shape of your distribution. And so often it's done by groups that want to, show a certain trend is happening even though it's not really happening. So like policymakers who want to show, improvement, or groups who want to hide a trend. So like a new government might want to downplay the perceived increase in crime or unemployment when they first enter office. So you do this by like either zooming in or zooming out. And so we would change this, like the levels that we have here and sort of the spread. If we wanted to make this look like basically everybody was the same, we could zoom way out on this and have like, instead of 160 at the top, we have like 1,000 at the top or like 800 at the top. And then it would look more like everybody's down here. Or if we had like just a little blip in something and you wanted to exaggerate it, you would zoom in. So you would like zoom in on this, on the y-axis here, and you would make it so then, really just a little blip would like be zoomed in, and if you change the scale on the side to like, instead of being 20 points between each one, you made it like 1 or 2 points between each of these, then it would like really make it seem like something was bigger. So, and you can do that with frequency polygons, you can do that with histograms, you can do that with bar charts, you can do that with any of these, where if you change the scales on either this, usually it's the y-axis that you change the scale, but you could change the scale on the x-axis too if you wanted to make things look like it was, almost everybody was right around the same kind of measure. So that's why you got to be careful about how you interpret any type of graphs like this, that if you see, make sure you look at what those scales are and that they're not trying to either overinflate something or make it look like something is there that really isn't all that big of a difference, or that they're looking to make something that actually is a big difference not look like it's actually a difference. So you got to just make sure that you really are knowing what it is you're looking at, and you can tell that whether it's being used properly or whether it's not being used properly. Typically, when you want to use a graph like the histogram or the frequency polygon, you want this scale to be enough to incorporate everything, so everybody gets to fit in there, all the points will fit in there, but you don't want the top to be too much higher than your highest point, because you want it to be a nice distribution to show what's going on. So be aware, be wary if you see something in, some kind of report or a newspaper article or something, and it's like, oh, everybody's like really down low. Well, like, what is the scale? Is the scale actually a meaningful scale, or are they trying to make it look like it's not, as big of an increase as it is, or whatever? So just something to be aware of. So when we want to show frequency distributions, often we want to group our data. So we're talking within a single variable here, but a frequency distribution would basically be where you're saying, well, how many are at each level? Well, if you have a continuous level variable, then it becomes difficult to be able to really use a frequency distribution with just giving every data point for every possible level. Now, it's not very difficult if you have frequency distributions for variables with just a few values. So you have like maybe dichotomous variables, like yes or no kind of answers, or variables looking at something like gender that might have only like 3 or 4 categories depending on how you're categorizing. If you only have a few values like that, it's pretty easy to sort of just present them all and say, what proportion are saying at what value, and then you're good. However, if you have too many values, then typically you want to group the frequency distribution. And so, for example, if you asked people their age and people just gave you their numerical age, then you're going to have to be like, well, there were this many people who were like 17, this many people who were 18, this many people who were 19, and maybe you have to go like all the way up to like the oldest person in your sample is like in their 60s. Well, then that's like a lot of information to just give if you're giving every single possible value. So often if you want to summarize that information in a way that's easy to read, you want to collapse those groups into categories. And so there's 2 reasons that you want to group, and you want to make sure that it makes sense for both of these reasons. And the first is that you have too much to read for an easily readable table. And typically this is around like anywhere from 15 to 20 values or more. then that becomes too much to read in like one single, just like look at the table and see what's happening. So typically then you want to group it because there's too many. But also the reason that you should want to group it is it's because it's going to make the distribution more clear or more meaningful if you combine and sort of collapse some of those values into categories. So you don't want to do it just because there's a lot. You want it to actually, because you don't want to hide information either. So you don't want to collapse things and then make it seem like it looks a way that the data doesn't actually look. So you got to be careful of that too. So you want to make sure that it's, you're doing it because there are too many values of your variable, but also because it's going to make it more clear and meaningful to see it with collapsed categories. So guidelines for when you're wanting to do grouping the data within frequency distributions. Again, this is just for one single variable. So the categories then you want to be logically defensible, so it makes sense to put those together, and it preserves the shape. So remember, we have the shape of our variables. If it's a bell curve, let's say, if it's a normal distribution, you want to make sure that when you say we're using the age distribution, we have an age variable. If it's like that nice bell curve, and if you start grouping things and it makes it look like maybe that there's like two peaks and then a valley in the middle, that's not representative of what actually it looks like. So you want to make sure you preserve the shape even once things are in categories. You also want the categories to be mutually exclusive and exhaustive. So that means that it's mutually exclusive in that each data point can only fit in one of those categories, but also each data point can fit somewhere. So with your age distribution, you want to have, maybe you'll have like a 20 and younger kind of category, which includes everybody 20 and younger, but then you have like a 21 to 30 and then 31 to 40 and then maybe like a 41 to 50 and then like a 51 plus or something like that. However you do it, you want to make sure that each data point can only fit in one of those categories, which is why you wouldn't have like 20 to 30 and 30 to 40, because then 30 would be able to fit in either one of those categories. You want to make sure that it's mutually exclusive, but also there is a spot for everybody. And then you want each interval width should either be the same size. So if you're going like for age, maybe you want like 10-year interval widths, or it should contain the same number of cases. So whichever is going to make more sense. So you might actually have, if you look at your age distribution, you might have a lot of people in like their either, late teens to early 20s. So maybe you want actually smaller categories for there because that's like half of your sample is there. And then you're going to have sort of wider age categories to sort of encompass similar numbers of people moving up the age, up your age categories. So you can do it either way. Either you're going to have the intervals just being the same, or it's going to have about the same number of cases in each interval. But either way, you want to still go back to make sure it's logically defensible and it preserves the shape of your data. And so you want to make sure you choose the number of groups carefully, because you want to still have enough spread to be able to see the shape. So you don't want to just collapse like 40 or 50 different data points and different values into like two groups. That might that's going to totally get rid of any of the shape that's there. But you don't want so many that you're like, well, I'm going to collapse this from like 40 to like 35 to make it a little bit easier to see. That's not much better than if you hadn't grouped it in the first place. So you want to make sure that you have enough intervals that it's actually summarizing the information, while at the same time having enough that you're preserving that shape. And so that would be sort of the way that you would use this to really be able to see the shape of again, a single variable at a time, without it being like too much to sort of encompass in one chart.